now let's talk about the moment of inertia, right? What is the moment of inertia based on what we talked last class? What is your perception of it? In relation to what we studied before, like, Newton's law, yeah. It's like a resistance, right? Like, for instance, here, this car definitely has more mass than this one here, right? So, if I want to start this car to be in motion, I apply here a little short impulse and, it start moving, right? Now, if I wanted this one to go at the same speed as that one, so what do you think I would have to do? Is it harder or easier to get this one moving or this one moving? It's going to be harder to get this one to move at the same speed as the other one, right? Because it's this resistance, the mass here, we have more mass here, so it's going to offer more resistance to change its states of stationary condition, or if this is already moving, to stop is also going to offer more resistance than this one. Do you guys agree with me on that one, right? Am I saying anything that is not logical? Sometimes we need to ask ourselves, right? Does this make sense or not? So it does make sense in a linear motion that since this one has less mass than this one, it's going to be easier to start motion on this one and to stop than this one, right? Because this one has more mass. Now, moment of inertia is, let's say, the cousin of mass in the linear motion, just that now this cousin lives in a different country, right? Here we talk about circular motion, and here we're talking about a linear motion, okay? When we relate to linear motion, if I have a little sphere and I have a string attached to it, which one you think is easier to start moving? If they have the same mass, if one string is longer than the other one, which one you think would be easier to start the motion? Which one? The small one, right? Let's see if I have that thing here. I used to carry that in my bag. Oh yeah. So let's say this one here is long. So you see, I have to bring my hand. I have to apply more. It's more effort. Then I have this one here. It's so easier, isn't it? So as this thing starts to increase, it's harder to have to apply. It's because of this distance, right? So, moment of inertia is a measurement of how difficult it is to start this rotation motion. Even something that has the same mass, like this little sphere here, right? So, how are we going to measure that? It is related to the radius and the mass, okay? So a simple particle would be, going on a circular motion, would be the radius, right? This distance to the axis, and the mass. But the radius squared, okay? That would be the moment of inertia. Now, this would be this situation here. And I think I'm going to even write that down there. I didn't write that, but here, the moment of inertia is going to be mr squared. It's that simple. Okay. Now, when I have a solid, like a rod, like here, then I have to count each little piece here. Take that into consideration, okay? And by using some calculus, the sum of all those would come up with a formula that is 112 mL squared. L is the length of that rod. You have to pay attention that where the axis is affects the moment of inertia, right? So if I'm trying to rotate this like that, if I have an axis here, it's going to be different if I try to rotate this here, right? So it's different effort depending on the axis, right? This here is harder than this one. Why I'm saying this is harder? Can you tell me why?
Because the center of mass is different for both of them when we're pushing.
Yes, but if I say this moment of inertia is larger than this one, why I'm saying that?
Because the only coefficient that changed was 1/12 and 1/3, which is a large difference.
The formula itself is same. This number here is smaller than this one, right? This is only 1/3. This is 1/12. So it's much easier to get this thing rotating, right, than this one here. Right? I could say, well, you know, this thing is hanging there, right? It's harder already, offer more resistance than this one here that is already kind of in equilibrium in order to get this rotating. It's like the ball, right? Like a basketball, right? Some of you, I know, are very good at playing basketball, right? When you rotate the ball, you can hold the ball like this and balance out. Could you do that from this side here? Hold it like this, you know, it would be kind of awkward. The ball would be like going like this, right? And would be much harder, right? So don't worry about the formulas. This is, you're going to make a table with your formulas, or if I'm going to use this in a problem, I will give the formula to you, okay? The formula is going to be given. So now let's calculate here. What is my marker? Oh, it's here. Good. So let's say this here is S, the distance. This is a square of 4 different objects there, right? They all the same. They all have the same mass, okay? The same mass. And now I want to calculate the moment of inertia for different axes. Axis A, axis B, C, and D. D, an axis that is going perpendicular to the board. So let's calculate the first one for A. Okay? How do we do that? So the moment of inertia is equal to the sum of masses Ri squared. So we have, when I have A, I have how many masses? I have 4, right? So it's going to be equal to 4 M, and what is R? This is a square. This here is S. So what is the value of r for the axis A? You know?
Is it S over two?
Yes, s over 2, because this here is s, this distance here is s over 2. So s over 2 squared. Okay? Now when I square this 2 is going to be 4, it's going to cancel with this one, so moment of inertia of A, IA, is going to be equal to ms squared. Okay? So can you guys help me now to do for axis B? What do you think is going to happen? Again, the sum IB is going to be the sum of MI RI squared. So what do you think? Can anybody tell me what to do?
You have the four masses, so it'd be 4m.
4, but the axis is right here, right?
Mm-hmm.
So I have to add each one. This one times R, this one times R, this one times R, but what is the value of R for this one?
S.
Huh?
Just S.
To the B axis, 0. Okay, for the A axis, you told me was S over 2, because that's the distance from here to here, here to here, here to here, here to here, 4 times. That's why I have 4 times ms over 2 squared. Is that okay? Now, when I have now the axis here, I'm talking about these 2 masses with this distance, and these 2 masses with the distance is 0, so that part of it is going to cancel. Right? Because the sum means m1 times r1 squared plus m2 times r2 squared plus m3 times r3 squared plus m4 r4 squared. Yep, that's the sum, right? I have 4 masses, I have to add the moment of inertia of each one of these masses here. But when I have axis B that is going through 2 of those masses, though that moment of inertia there is 0. Yes? Because moment of inertia is what? Mass times the radius squared. So here, in this case, now I'm going to have 2m s squared. Right? Agree? Everybody? Yeah.
It's because the 2 masses on the B axis can't move any distances, so it has to be 0 something.
Exactly. It's not rotating at all, right? It's just rotating themselves, but it's not along an axis. What is the torque there? It's 0, right? Is that okay? So now let's do the axis of C. Moment of inertia to C, again, the sum of masses. But now I have 2 masses again on the axis, and I have these 2 here. So it's going to be 2 times m, but what is this distance here now? What is the radius now from the diagonal? Negative? No. If I have a square, right? This side is L, this side is L.
Oh, never mind, I was wrong. You have to do a Pythagorean.
Yes.
Okay.
So this here, what is this diagonal? Is L what? Square root of?
S over 2 squared plus S squared.
Yeah. So if you want to do it, so let's say, I'm going to call this D, so it's going to be D squared equals L squared plus L squared. So D squared is going to be 2L squared. So D is going to be L square root of 2. You guys don't remember that? So this here is going to be S square root of 2, but it's only half of it, so I need to divide that. S square root of 2 divided by 2 squared. Is that okay? So when I square this guy, it's going to be 2. When I square this guy, it's going to be 4. 2 over 4 is 1/2. I have this 2 here, it's going to cancel. So this is going to be equal to ms squared. Okay? Now I have the last one, D. Now this axis is going this way, right? So if the axis is going this way, and I have 3 masses, but they are different distances, right? So what's going to be? I'm going to write down here, I of D is going to be equal to what?
MS squared, 2ms squared
2ms squared
plus
plus
ms square root of 2.
ms square root 2
Squared.
squared. So that's going to make this thing here is going to be 2, right? So I'm going to have I of D is going to be 2ms squared. This is going to be plus 2ms squared. So this is going to be equal to 4ms squared. Good? Everybody got that? So if this is in a test, you guys can do this one. All right, so let's review again torque, right? The definition of torque is the product of the distance times the force. Those are 2 vectors. This is a cross product. It is going to be a vector. The definition of angular momentum now is also a vector because it is a cross product between now R and linear momentum instead of force. Okay? It's good to look this here because now you can compare the difference between torque and angular momentum. So angular momentum is related to the linear momentum. Torque is related to the force. Okay? So a particle moving with a velocity v and has a mass, if it has a mass, it has a linear momentum. So this particle moving has an angular momentum. Okay? That's the first thing to see, because it has an angular momentum in relation to this point. Right? The distance times the linear momentum. Now remember, the magnitude of the angular momentum is the product, the cross product of those 2, right? sine theta, sine the angle. Okay? So if the angle is 90 degrees, sine of 90 is equal to
1.
1. So we have an angular momentum. If I have this here at 90 degrees, right? Now, if my point is on the same direction of the linear momentum, what's going to be the angular momentum? If instead of Q, this point, being here, if we're here, what will be the angular momentum? 0, right? It's 0 because the sign of 0 is 0. And it doesn't make any sense. What is angular momentum? It's related to rotation, right? It's this kind of a rotation from here because there is a torque there, right? This thing is going, that way, right? There is a rotation here. But if I'm here and this particle is moving that way, there is no rotation associated with that from this position, right? So it doesn't make any sense there. So linear momentum is mv. Now, if there is a rate of change in the linear momentum, right? Rate of change, so it's going to be a rate of change on the velocity. But rate of change of velocity is acceleration. So the rate of change in momentum is related to a force. Remember I was saying here, this thing will continue a constant linear momentum unless I apply a force here, right? It's not going to change. Momentum is conserved unless I apply a force. That's what this means here, okay? If this here is equal to 0, the rate of change of momentum is equal to 0, that means that momentum is being conserved on the system, right? Now, if I multiply a distance here, if I'm now having a point Q that has a distance to my mass, and I multiply that here, right? And I multiply this side because this is equal to force. If this is the change in momentum, the rate of change in momentum is equal to force. If I multiply R on both sides, this side I'm going to have torque. And this side I'm going to have rate of change in momentum. So rate of change in momentum has to have a torque. If torque is 0, what happened to angular momentum? It's not changing. So this is when at the beginning of the class I asked some students to hold this thing when this thing was rotating, right, this way. So there is an angular momentum in this direction, right? And this angular momentum is conserved, it's not changing. And there's no torque here. Now if I apply a torque like that, remember what happened. There was a movement. She was going on the other direction, right? She was rotating. Because now she was applying a torque, and in order to balance out, she was going in the other direction. Because the torque was, she moved the torque this way, so she was going in the other direction. So that's what it means. If I don't apply any torque, angular momentum, if I want to change angular momentum, I have to have a torque. And that's what she did, okay? So from these formulas here, we relate that angular momentum is R times linear momentum, and I convert this V into the angular speed, so I have now mr squared times the angular velocity. instead of mRV, I put now V equals WR, angular momentum times radius. So now I have isolated this here as the moment of inertia times the angular velocity. Okay? Now when I find a rate of change here, rate of change in angular momentum is rate of change in the angular velocity, so that makes the angular acceleration. So torque is equal to angular acceleration and times the moment of inertia. Like force is equal to mass times linear acceleration. So they kind of equivalent here. If I write here force, this would be ma. So m is the resistance on linear motion. Moment of inertia is the resistance on angular motion, circular motion, right? So that's, you know, the parallel that you can make between torque and force. Is this, okay? So this here is very important because now, today in the experiment, you're going to use this formula here, that angular momentum is conserved, right? So if I change the, if angular momentum is conserved, if I change the angular velocity, I have to change the moment of inertia. Do you see that? If L is conserved, if I change W, I have to change I. If I increase W, I have to decrease I. So what do you think is going to happen in this experiment here? That I have, what is it? This one here, right? If this thing is rotating, going that way, or it doesn't matter. If I drop another object there, what do you think is going to happen? This thing is rotating. I drop,
That object will start rotating with it?
the object will start rotating with it now, but what happens to the angular velocity? It's going to increase or decrease?
Depends on where you put it.
Huh?
It depends on where you put it.
It depends on where I put it. How can I, if I drop something there now, you have more mass there, you have more moment of inertia. So what happens to the angular velocity? Well, you guys are going to experiment there, and you're going to be able to see what happens, okay? So let's have a break, and then we do the experiment.